Hello, welcome back to Mech 416/816 Engineering Acoustics. In this video, we're going to continue our discussion of the linear acoustic wave equation, starting off with the equation of state. We will then go through the equation of continuity and then briefly talk about the linear Euler's equation. And then in the next video, we will combine those three together to derive the linear acoustic wave equation. Okay, so starting with the equation of state, first the fluid must be compressible. If the fluid is not compressible, then it will not be able to support a change in pressure. And then going a step further and assuming that we're dealing with an ideal gas, the pressure is then going to depend on the density. So as the pressure changes, the density is going to change. As the density changes, the pressure is going to change. From there, we can expand the total pressure using a Taylor series with respect to that density. So we start with our total pressure, big P here, and that's a capital P that I've written, not a vector, is equal to P0, that atmospheric pressure, plus partial big P over partial rho, evaluated at rho 0, where rho 0 is the density at atmospheric pressure, times the quantity rho minus rho 0, plus higher order terms that depend on rho squared. So rho here, this is our total density or instantaneous density. So it includes the atmospheric density plus fluctuations. And then rho 0 here is the atmospheric density. So changes in pressure and density are going to be small. As we talked about and briefly showed in the last video, acoustic pressure waves are going to be small fluctuations about the atmospheric pressure. So this means that we can neglect the higher order terms and then write that big P is equal to the atmospheric pressure plus partial big P over partial rho, evaluated at rho 0 times the quantity rho minus rho 0. Again, we're neglecting higher order terms here. We can then rearrange this to yield the following. We can get the total pressure P, big P minus P0, that's going to be our acoustic pressure, is equal to the quantity rho 0 times partial big P over partial rho, evaluated at rho 0, times the quantity rho minus rho 0 divided by rho 0. And let me rewrite that fraction there. Okay, so the quantity here shown in the curly braces is called the bulk modulus. The bulk modulus, and we'll represent it as capital B. And the quantity on the right here is the condensation. And that's just what it's called. And we'll represent it using the letter S. And so then we can write that the acoustic pressure, small p, is equal to the bulk modulus B multiplied by the condensation S. And equation 7 here, this is the equivalent of Hooke's law, but for a fluid. So this is Hooke's law for fluids. Okay, now for the equation of continuity, we're going to consider a differential volume element shown here. Let's go ahead and draw our directions. Vertically, we're going to have the z direction. In this direction, we'll have x, and over here, we'll have y. So then the differential element sizes are going to be dx, dz, dy. And then we're going to consider the rate of mass flow into the element over here, and then the rate of mass flow on the other side as well. In this case, we'll have rho x, rho times ux, and that should not be a subscript. Let's make that a superscript representing the fluid particle velocity in the x direction. And then on the other side, we're going to have rho times u superscript x. Let me rewrite that, superscript x, plus partial of the quantity rho u superscript x divided by partial x times dx. So this is just for the x direction. You can do similar things for the y and z directions, but we're going to skip those. We're going to focus right now on the x direction, and then we will produce similar equations for the y and z directions, and which we won't do that live. If you want to, you can do that offline. In fact, actually, probably a good mini homework, which we'll have due on. So this would be mini homework 5, I believe. We'll have this due on, let's say, in class on March 5th. Would be for you to verify that what we derive here for the x direction is also the same in the y and the z directions. Okay, but anyway, for the x direction, we're going to get the following. We'll have the quantity rho ux minus quantity rho ux plus partial of the quantity rho ux divided by partial x times dx, all of this times dy dz is then equal to minus the partial of rho u superscript x divided by partial x multiplied by dv. Like I said, you can find similar equations for the the y and z directions, and this is what you should do for that mini homework. You do that, and then combining them all together, we can find that the total influx of mass into the element is the following. We get that the quantity minus parenthesis partial of the quantity rho ux over partial x plus partial rho u superscript y over partial y plus partial rho times uz divided by partial z, all of that times dv is equal to minus del, which is a vector operator, del dot the quantity rho times the fluid particle velocity u dv. And if you're not familiar with this del operator, that is something you should look up and look into. Okay, so then the rate at which the mass increases in the volume is partial rho over partial t times dv. Combining these results, what we can find is that partial rho over partial t plus del dot rho u is equal to 0. And this is our continuity equation. We're going to box this equation. Again, this is what we call the continuity equation. from here, what we can do is we can let rho equal to rho 0 times the quantity 1 plus S, where S is the condensation, and we assume that rho 0 is weak in time. That means that the atmospheric density remains constant or changes over very long periods of time. And then we assume that S is very small, and then we can write that rho 0 times partial S over partial T plus del dot rho 0 U is equal to 0, and that is another expression of that continuity equation. Okay, we're now really briefly going to talk about the linear Euler's equation. In fact, we are only just going to write it down, and then you should read section 5.4 for our full derivation and explanation of what this equation is. But the linear Euler equation is quite simply going to be rho 0 times partial U over partial T, and then this is equal to minus del acting on our acoustic pressure P. Okay, so in the next video, we are going to combine these three equations and produce the linear acoustic wave equation.